All right, so this is the last section we're doing relating to vectors, right? Called the cross product of two vectors. Remember, we have basic vector operations where add, subtract, multiply by a scalar or constant, right? Then we found there was a new one, which was called a dot product. And dot product we were able to do in the plane on a flat surface, and we were able to do it in 3D. But this is one you only can do in 3D. It does not work in 2D. That's why it's not addressed. Okay, we did that. So I wouldn't get too concerned about all this here because when you look at it, it probably doesn't make a lot of sense. This is their explanation of it. When I show you on the next couple slides, you'll see the mechanics of it actually make it seem it's not that complicated to calculate. I mean, besides the fact that they're showing it the way they are here, they're using all the linear combinations of the standard unit vectors, which tends to give us a little bit more trouble than if we just use the component forms. Right? So again, don't get hung up about that. Right? Remember, we did this a little. We didn't do this a lot, but when we did matrices, we talked about what's called the determinant. And the determinant, you can do a determinant for bigger than 2 by 2, but the only place we ever see a determinant is usually with a 2 by 2 matrix. Right? And the reason that we did it is if you had a matrix like A and you wanted to know the inverse of it, then you would do this. Okay. The inverse would be 1 divided by the determinant, and then you would have inside, you would switch these two, so it'd be B2, and you don't need to write this down. I mean, this is just trying to show you where this math comes from. And then you put minus signs in front of the other two. Right, but in order to do the determinant, this was the operation that you have to do. You do, right, this times this, A1 times B2, minus A2 times B1, right, along the diagonals, right? This times this, minus this times this. That's the math, right? In the end, it's not that hard of a thing to do, right? So remember that operation. And now we'll go back to finding the cross product of a vector. Now, I'm going to show you up here, and then we can look at what they've got, which is the same thing. Okay. First, you're going to write, it matters, and we're going to see why. We're going to see it matters the order you write these. If I do U cross V, and again, the cross means cross product. Again, that's why you might think, oh, that's like multiplication. Yeah, but the dot product kind of looks like multiplication too. Neither one is multiplication, right? It's something a little bit different. But you've got, if you're going to do U cross V, then you write U on the top and V on the second row like that. Now, the result of a cross product is another vector. So these are two 3 by 3 vectors. We're going to, or sorry, 3 component vectors. We're going to get a 3 component vector for our answer. Right? So for the first component of the answer, cover up the I, right? And then do the determinant kind of thing with these 4. U2 times V3 minus V2 times U3. That will be the first component. That's this right here. I mean, if you want, you could have done it in component form. U2 V3 minus U3 V2. That's the first component. So since it's the first component, you just try to remember, you're covering up these 2 because they're the first component. Do the determinant kind of thing with the other 2. Okay. Now, for the second component, cover up the second, right? And you're going to do the same thing. Now use what's left to do a determinant operation. U1 times V3 minus V1 times U3. Right, the same kind of thing. Now there's one difference. For the middle component, there's a negative in front of it. Right, so you got to go like this. Negative U1 V3 minus U3 B1. Right. For the last component, cover up the last column and do the determinant operation. U1 times V2 minus V1 times U2. That's that right there. Right. And so that's the component form. They wrote it as the linear combination of the standard unit vectors. But in the end, for every component, you do that determinant kind of operation, right? This times this, minus this times this. This times this, minus this times this. Put a minus in front of it. This times this, minus this times this. That's how you do a cross product. Now, they're showing the same thing here, right? For the first component, they covered this up, they did the determinant. This one, they covered those up, did the determinant. Cover that up, do the determinant. So I think it's easier to, once you see it how it works, you won't be as confused by all of this or what was on the previous slide. So in terms of just calculating, let's calculate. Here's two vectors. And honestly, you know, I probably, for myself, Josh, right? I would write it in component form because I just find it easier than having the I's, J's, and K's. Especially, you know, for them, it's easier because they can just write their letters in bold in the textbook, you know, but we always got to, if we're going to use the I, J, and K, you got to have little vector symbols to indicate they are vectors. Right, so what would be the component form of this vector, of U right here? 1, 2, 1, right? So the U is 1, 2, 1. And how about B? Right, 3, 1, 2. Okay, so U cross V. Right, the first component, cover up the 1 and the 3 and take the determinant of what's left. What do you get? 2 times 2 minus 1 times 1, 3. Okay, for the second component, cover up the 2 and the 1 in the middle. Right, now it's, in fact, let me do this. It doesn't quite work, but works a little. Yeah, you cover those up. And now do the 1 times 2 minus 3 times 1. Right, now we move it. For the third component, cover that up and do the determinant. 1 times 1 minus 3 times 2. Right, so this is 4 minus 1 is 3. 2 minus 3 is negative 1, but there's a minus in front, so it's positive 1. And 1 minus 6 is negative 5. Okay, now let's see what happens if we do the V cross U. Okay, we'll switch the order of it. Let's see what it does to the answer. So I'm going to do that right here. V equals 3, 1, 2. U equals 1, 2, 1. Right, so U cross V, sorry, V cross U equals Okay, let's do the, what do I got wrong here? I'm on the wrong thing. Oops, over here. Okay, so now do the math. 1 times 1 minus 2 times 2. 1 minus 4, negative 3. Move it over. 3 times 1 minus 1 times 2. Right? That would be 3 minus 2 is 1, but there's a minus in front, so it's negative 1. Move it over. Not very straight, but, right? 3 times 2 minus 1 times 1. 6 minus 1, 5. Okay, what do we notice about these two? Yeah, I mean, also because we did that in the homework last night too, right? How do you make a vector opposite? You just multiply it by negative 1, right? Okay, well, that's exactly what happens here. If you switch the order of the cross product, you get a vector which is in the opposite direction. Well, that comes up on one of the next slides as a property, right? U cross V equals negative V cross U. Good. Good. Angelina? Okay. All right, now we'll do the third one. V cross V. Let's see what happens if we do a cross product of a vector with itself. So V equals 3, 1, 2. And since it's with V again, I'll write another 3, 1, 2. So let's try our V cross V. Right, so I'm not going to mess with the rectangle. Let's just, in your mind, picture we've covered up the 3's, and now do the determinant operation. 1 times 2 minus 1 times 2, 0. Okay, cover up the 1's. 3 times 2 minus 3 times 2, 0. Yeah, good one. Okay, next one. 3 minus 3, 0. Right. So what do you get if you take the cross product of a vector with itself? 0. Because I mean, it's not going to be particular to this vector. You could say that would be true of any vector. If you've got these are the same, that would happen. It's actually not just that. What if I have, let's say, I'm going to do a cross product of V and 2V. Right? Let me make a parallel vector, just a multiple of the other. Right? So here's V, 3, 1, 2. And then this is 2V, which would be 6, 2, 4. Okay, now what happens if I do V crossed with 2V? Right, so I cover these up. 1 times 4 minus 2 times 2, 0. Cover up the middle. 3 times 4 minus 6 times 2, negative 0, right, Pierce? Okay. And cover up the left. 3 times 2 minus 6 times 1, 0. So it's actually not just when you do a cross product of a vector with itself. If you take a cross product of a vector and a parallel vector, you also get the 0 vector. So we have a lot of properties which relate to cross products. Right? These are the algebraic properties, of which we already looked at this one and this one. What does the second one kind of remind you of? Kind of looks like a distributive property, right? So that would hold for cross products. The next one is kind of like the one we had for a dot product, right? If you multiply a cross product by a constant, you could either move that constant on one of the vectors or the other, but not both. right? U cross with a zero vector equals 0 cross with the vector u equals a 0 vector. If you cross that, and this makes sense, right? If one whole vector is 0, 0, 0, it's going to zero out everything. And here's one. U dotted with v cross w is the same thing as u cross w, or sorry, u cross v dotted with w. So if I move the parentheses, the operation changes. What is the result of, if I do u dotted with v cross w, what is the result? Is it a vector or is it a scalar? Well, if in parentheses, when you do the cross product, what is the result? Cross product is a vector. So now you're taking a dot product, and the result of a dot product is a scalar. So it's scalar. Okay. Now, the geometric properties, and the reason why we look at this at all, is that when you take the cross product of a vector, you get another vector which is orthogonal to both of the ones you started with. Right? U cross V is orthogonal to both U and V. And that is, you know, how we set up coordinate space when you're not doing everything in perfect X, Y, and Z space, which things are not. But when you need to find the orthogonal, you're going to take a cross product. So this is kind of the main reason why we're doing this stuff, because of this geometric property. Right. The second one gives us another way to find the angle between two vectors. Right. The magnitude of the cross product equals the magnitude of u times the magnitude of v times the sine of theta this time. Remember, we had a similar formula with dot products. Right. It was the cosine of theta equals u dotted with v divided by the magnitude of u times the magnitude of v. So which one do you think would be easier if you were told, find the angle between two vectors? Would you rather find it this way or find it this way? Honestly, I like using that one better. I think cross product is way harder to calculate than the dot product. But they both will get you at the angle between two vectors. Okay, here's the one we did about parallel. U cross V equals the 0 vector if and only if they're scalar multiples of each other. Scalar multiples of each other means they are parallel. Right? So if you, that's the check, right? If you take the cross product and you get 0, you know those two are parallel to each other. And the magnitude of the cross product of two vectors is the area of a parallelogram that has u and v as adjacent sides. So if you can imagine, if u is here and v is there, if I extend out like that, you know, get that u over here and the v up there, then that's a parallelogram. And the area of that parallelogram is the magnitude of the cross product. So first do the cross product, then take the magnitude. Now I wanted to show you this. That looks pretty confusing, right? There was a really good program on PBS last Wednesday. It's one of their Nova, and it was it's The Great Math Mystery. And it was as good of a program as I've ever seen that just kind of like explained why math is important. And it got into math and physics and engineering and all kinds of stuff, music. It was very interesting. Part of it, which I probably learned at one time but didn't remember very well, was what they called Maxwell's equations. And Maxwell was a physicist in the 1800s who's the one who basically, because electricity was just coming about at that time, they realized that there is actually a perpendicular relationship, orthogonal relationship between electric fields and magnetic fields. And they're explained by this right here. And if you notice these 4 equations, which we can't even begin to understand most of what's in here, but you definitely see things that we've done already in this class, which is dot product, cross products of vectors. I mean, that's where it comes from. So, I mean, the whole, this stuff right here, in the end, it's, what comes after Maxwell and his equations, Marconi and radio, right? The idea that actually there are these electromagnetic waves out there that you can send signals over, and it's because of this stuff here, vectors and this kind of stuff here. And eventually, hey, our cell phones and that kind of stuff, they're all using the same stuff that came out of this. Okay, so here's a few examples. What time is it? 20 time. Use the cross product. Find a unit vector that is orthogonal to both u and v. So when you get that kind of a question, in your mind, you've got to be thinking to yourself, oh, they want the cross product. It's not likely that they're going to give you the problem and say, find the cross product of these two vectors. It's just as likely that it'll be this. And then you just understand that to mean, oh, find the cross product. So basically, what will we get when we take the cross product of u and v? What is it? We will find a vector which is orthogonal to u and v, right? But that's not exactly what it asks for. It asks for a unit vector which is orthogonal. So once we found our vector which is orthogonal, what do we need to do with it? Divide by magnitude, right? So first let's do the vector. Now notice that there's 3 components on the u, but there's only 2 on the v. So when I set this up, right, the u is going to look like 3, -4, 1. And the v, that's a bad v. What are the components of v? -3, 6, and 0. Right, so u cross v is the first component, cover up the first column, -4 times 0 minus 6 times 1, -6. Right, 0 minus 6. Cover up the middle. 3 times 0 minus -3 times 1. See, that would be 0 minus -3, which is 3, but the middle component has a negative in front of it, so -3. And then the last, cover up the third, 3 times 6 minus -3 times -4. 18 minus 12. 6. Okay, so what is the magnitude of that? The square root of -6 squared plus -3 squared plus 6 squared. What? That's 36 plus 36 plus, that's correct, 81, which is 9. So the unit vector, is -6 over 9, -3 over 9, 6 over 9, which of course we would simplify as -2/3, -1/3, 2/3. Good. Okay. Show that the quadrilateral with the given vertices is a parallelogram, and then find the area of the parallelogram. Right. What do you have to show that a shape is a parallelogram? That the, say again? The sides are parallel, right? So in order for them to be parallel, they have to be the vectors. If you make the vectors, they've got to be scalar multiples of each other, let's say, right? So let's say if I want to know if this side is parallel to this side, then using these as the initial and terminal points, let's just find the vector. Right? So let's say, what is this vector here between DC? I'll call it like this. DC with an arrow on the top equals 7 minus 6, 2 minus 5, negative 3, 4 minus 0, 7 minus 6, 1. Okay, let's try this side. AB. 2 minus 5, 6 minus 2, 4, and 1 minus 0, 1. Okay, so we've shown that. Now we need to show that these are the same. So that I'm going to use AD, right, in that order. AD. So subtract. 5 minus 5, 0. 0 minus 2, 6 minus 0, 6. Okay, do the same thing on the other side. BC. 2 minus 2, 0. 4 minus 6, 7 minus 1. So, they're not only scalar multiples, they're equal to each other. So yeah, these are parallel sides, so this is the parallelogram. How do we find the area of the parallelogram? The magnitude of the cross product. So you want to take one of, at some point like here, then this is AD and this is AB, then we're going to take these vectors, that one and that one. Do the cross product, take the magnitude. So let's see. I'm just going to write them like this. 0, negative 2, 6, negative 3, 4, 1. Right, the cross product is cover up the first. Negative 2 minus 4 times 6, negative 26. Right, cover up the middle. 0 times 1 minus negative 3 times 6. Right, that's 0 minus negative 18, which is plus 18, but there's a minus in front of it. And cover up the last. 0 minus 6, negative 6. Okay, and the magnitude of the cross product is negative 26 squared plus negative 18 squared plus negative 6 squared, which is what? 32.2. Right? So that's an area of a parallelogram. The last example is this. We good on that? Now it says, oh, I thought I was going to need 2 slides for that. I didn't need that. Find the area of a triangle with the vertices A, B, and C, as stated. And they've even got the picture right there. So did you see anywhere in those properties that said, here's how you find the area of a triangle? So how are we supposed to do that? What is it that we can find the area of that we just did? A parallelogram, right? But if you have any old parallelogram, right, and you divide it in half, what do you have? 2 triangles. So that's the theory here. That we can, if we use 2 vectors as the corner points of a parallelogram, we'll find that area. And then what will you do with the result? Divide by 2. That's it. So it's going to be the same math. This time we're just going to divide by 2 at the end. So let's say we need to come up with two vectors. And it doesn't matter which ones. How about I'm going to do BC and BA, right? Those two. Right, so the BC is 4 minus 5, 1 minus 4, 5 minus 6. Okay, now let me do BA. Okay, 4 minus 5, 3 minus 4, and 0 minus 6. So those two vectors come from this. They both start at A, or sorry, they start at B. So that would be the corner points of a parallelogram. Now we do the cross product. -1, -3, -1 crossed with -1, -1, -6 equals. Cover up the first. 18 minus 2, right? 18 minus 2, 16. Cover up the middle. 6 minus 1, which is 5, with a negative in front of it. Did I get that wrong? Yeah, you're right. Yeah, it should have been 18 minus 1. I think I do that every year. Okay. So that should have been 18 minus 1, 17. And the last one, 1 minus 3, which is -2. Okay, so if that's the cross product, right, then we take the magnitude of that is the square root of 17 squared plus -5 squared plus -2 squared. Now, hopefully I didn't already make a big mistake there. 17, 5, it's all correct, which is the square root of 318. No, 289 plus 25 plus 4, okay. Which is what? 17.8. Now that's the area of a parallelogram, right? The area of the triangle would be 17.8 divided by 2. 8.9. Okay. That's it. Cross products. Not even too much homework. 8 problems.